Hi everyone, this is Yash here, and I welcome you to another 0 to 1 webinar series. Um, Today we have folks from SupraOracles. We have Vinny and we have Nolan from SupraOracles who will be taking us through how to build your own crypto price feeds using SupraOracles. So, Vinny and Nolan, can you guys hear me and you'd like to introduce yourself?
Yeah, can you guys hear me?
Yes, sir, we can
Yep.
hear you.
Okay, great. Yeah, I'm Vinny with SupraOracles. I'm the director of Can everyone mute themselves? Thank you. Yeah, so I'm the director of ecosystem here. I lead the business development team, and I also work with dApps, mostly DeFi and GameFi, to help them implement our Oracle price feeds and VRF random numbers. On the event page on Luma where you guys registered, we have a link to our Discord. So if you do need to reach out for any reason, please just join our Discord and you can message me or Nolan or just ask your question in the general chat. Nolan?
Hey everyone, my name is Nolan. I'm a developer advocate over at SupraOracles. I'm working on a lot of guides right now, so at the end we'll share the links to our documentation. It'll show even more integration examples with our VRF and our price feeds. Just a heads up, I'm having some internet difficulties yesterday and today, so if I do drop off, just know I'm like speeding over to my modem to reset it, and I'll be back on as soon as possible.
Okay, great. Any other questions before we get started? Looks like we have about 99 people
I think
here.
I think we are ready to go.
Okay, great. I'm going to start by sharing my screen. And let me mute the Huddle 01 here first. All right, I think you guys can see my screen. So as Nolan mentioned today, we'll be going over what we call S value price feeds. That just means Supra's most representative value. And VRF, verifiable random functions, what they are, how to integrate them, why we need them, and the use cases. And after going through the high level and our documentation, Nolan is going to go through a tutorial of how to do a ERC 721 contract using these price feeds and our VRF service. So starting with S-value price feeds, what are they? You can think of them just as smart contracts that store some kind of data, and they're periodically updated on some timer, like a heartbeat or deviation threshold. So as most of you probably know here, blockchains can't natively call APIs. So price feed contracts and oracles are used to bring external data onto the blockchain to power use cases. You can think of the storage contract, this price feed contract, on-chain API to access that data. It's readily available for use. And the data can be anything that the feed operator decides it's going to be. In our case, it's going to be crypto price pairs. But later on, we're going to incorporate different kinds of data, such as FX data, NFT data. So price feeds can be broken down into two main functions. There's an update function and a view function. The update function is typically called by the managing party, in this case, SupraOracles, to update the data stored within that contract. And there's also an off-chain service that monitors the conditions for the feed to be updated. So as I mentioned before, there's a heartbeat or a deviation threshold. And then once those conditions are met, either from the timer or the deviation threshold, the Oracle will make the call to and then call the update function with the updated data on chain. The view function is called by the end user to basically pull contract from the feed, from the price feeds contract, pull data, sorry. And this is a view function. So a view function in Solidity promises not to change the state of the EVM, so it doesn't cost any gas. And of course, you can also use a JavaScript library like Web3 or Ethers if you want to pull that data from the smart contract to an off-chain. This is just a diagram here showing what we discussed. On the left, there's an on-chain portion with the update and view functions, and the Oracle and API sitting off-chain. So Supra is applying layer 1 consensus algorithms to the Oracle space. This is just a little bit about our architecture here. We have our white papers on our website. But when we go to Alpha Mainnet next month, we'll have nodes dispatched to 18 data sources. These are connected to WebSocket APIs. And then we have a calculation methodology to obtain the S value. I won't go into detail here, but if you want to learn more about our architecture, feel free to take a look at our white paper. And so something also unique about us is this unique architecture allows 100 to 200 data pairs to be signed in one block on Supra's native Oracle chain that's not public. But essentially, we are running consensus on all of our own data with a finality of 3 to 5 seconds before delivering it to destination chain's price feed contract. So this means there's one smart contract containing these data pairs on each network we support, and currently we're on 37 testnets. This is just a little visual about our architecture here. These are the individual clans made of nodes that are dispatched to each of the centralized data sources off-chain, and these are WebSocket APIs. So clans come together to form tribes. There are specific tribes for each type of data pair, and there's also parallel processing. So we have a strong security guarantee for our Oracle without giving up any speed. And the method by which we keep one of the methods by which we keep our Oracle secure is we actually use a VRF random seed to shuffle the network topology and randomize the nodes and clans dispatched to each data source. Just to jump into the code here, and this code is off of our docs, SupraOracles.com/docs. The link is also on the Luma page. So first, we have an interface to call it a check price function. This is the view function we talked about earlier. It accepts one parameter, which is the market pair, say Ethereum, USDC, and it returns two values, the price and the timestamp. You can declare this interface at the top of your file outside of your contract declaration. Or typically, developers will have a separate Solidity file just with this interface and then subsequently import it into their contracts that are using price feeds. And here's our contract. We are declaring the S value feed as the interface variable. And then in the constructor, we're binding the contract address to the S value feed variable. So where you would get this contract address is just in our docs. There's a networks page, and you choose the contract address of the network you're trying to deploy the smart contract on. So for example, here it's ETH Gurley. And this function here is the callable function of our interface variable. This is the view function we talked about earlier. And it's worth noting that, as I mentioned before, one single contract address that would just bind it allows you to query every single market pair available on that network. So currently we have about 51 market pairs available, and we're planning to support the top 100 very soon. We just renamed this view function get pair and made a slight modification. Here we have a parameter that allows you to pass a string. So basically, as I was saying, with this one contract, you can pass any string, ETH, USDC, Avalanche / Bitcoin, whatever market pair you want to query, and you can view the price for that. And as you notice here, this function returns a price and a timestamp, but we've just commented out the timestamp as we only want the price. This is just the final code snippet. This is available in our docs. You can actually just copy and paste this entire code snippet into your Remix or your preferred IDE and test out the view functions. This here is just a code snippet. As I mentioned before, you can use a Web3 library or an Ethers library and actually use the price feeds off-chain. It's also worth mentioning here that because Solidity doesn't support floating points, our feeds actually returns a point of precision, and Nolan will go over in this tutorial later how you can reformat this. So if you see something like this just means ETH price is 15.89 and change. So why do we need them? We want to have the Oracle price feed readily available for users to view anytime they need it. So this is a push-based model. We're updating these price feeds on a set interval, say every 1 minute. So this is a push-based model, not a pull-based model. Although we are planning to offer a pull-based model later on as well. And typically we work with DeFi, dApps, DEXs, lending applications needing on-chain payments. And once we offer different types of data feeds beyond crypto price pairs, this might open up some different use cases as well. So that was Oracle price feeds. Now we're going to move on to verifiable random functions. You can think of it as a random number generator for the blockchain. VRF is one of our services that generates cryptographically secure random numbers. They're generated securely, but also delivered to the blockchain securely. And the VRF, these random numbers are unbiased and unpredictable. They're tamper-proof and verifiable. And when I say verifiable, it just means anyone can verify that the random number generated by a VRF is valid. All they need to do is inspect the proof and verify the correctness of the hash output. So while only the holder of the VRF secret key can compute the hash, anyone with the public key of the VRF can verify the correctness of the hash. And that's why we call it a verifiable random function. And we'll go over later why you would want this property. So VRF is broken down into two primary functions: a VRF request and a response that delivers that random number. A request is called to generate a request for a random number. In this request, we also provide the VRF service nodes with a callback function. A callback function is where random numbers are returned, and typically where you have some code logic to use those random numbers. You can also set the quantity of numbers you'd like. Currently, you can request up to 1 to 255 random numbers in one request. And we also have a feature here where the user can configure the number of block confirmations to wait before the VRF service nodes pick up that request. The response is initiated by the VRF service nodes on Supra side. However, these nodes eventually, after Alpha Mainnet, are going to be open source, meaning anybody can sign up to be a node operator. So VRF service nodes consider it as an off-chain service that monitors the blockchain for these VRF requests. The nodes generate the random numbers along with the accompanying cryptographic proof, and then returns list of array of numbers to the provided callback function. And as I mentioned before, the callback function executes some code using these random numbers. This is just a diagram here going over the flow we just discussed. User makes the request. Super smart contract creates an input with a combination of the user's parameters and some blockchain information. And then some relay nodes fetch this input, forward it to our distributed VRF service nodes here, which calculate the VRF and then send it back the way it came, eventually delivering it to the callback function. So just to jump into the code here, we start with defining an interface. And as you can see, we have 2 overloaded signatures. Just to go over the parameters here, we pass the callback function signature, RNG count, that's 1 to 255 random numbers you want in one request. Number of confirmations to wait. Typically, if you're just testing or if you want your response pretty quickly, you just want to set it to 1 confirmation. But if you have a high value use case, you might want to set it to 10 confirmations just for more security. And in the top signature, we have an optional client seed parameter. This just provides an extra layer of security. It's optional. It just means at runtime, the VRF requester can pass a number that's used to calculate the input, and because you're passing a number at runtime, resulting in a different input, you're going to result in a different VRF response because it's deterministic. And this is used because nobody else can guess what you're going to pass as a number ahead of time. And the request function returns a UN 256, which is just a nonce. And you'll see in the subsequent slides, we're going to use this nonce to map the request to a username. So this is our contract here. Once again, you would go to our networks page and copy the network address of the network you'd like to deploy VRF request contract to. And here we have 2 mappings. Here we're mapping the nonce, which we'll use as an index to say a username, say Vinny. And then the second mapping here, we're mapping a username, say Vinny, to an array of random numbers. So you'll see later how this is used. And our first of our 2 functions is our request function. We're calling it get RNG for user, pretty self-explanatory. We're going to pass the RNG count, the quantity of random numbers we want, and the username. And in this example here, we're actually hard coding the number of confirmations to 1, and we're also hard coding the client seed. And we're using our interface variable here to generate that request, and using that mapping the nonce to the username. And this is our second function, our VRF callback function, which we also passed as a parameter during the request. And in this first line here, you see there's a guard clause, message.sender is equal to SupraAddr. So this just means only SupraRouter contract can deliver the random numbers back to this callback function. This is pretty obvious because you only want the VRF service provider to be able to return the random numbers, not just anyone. And so parameters here are nonce, and also RNG list here is just the array of random numbers being served by the request. And then the rest of the code here, we're basically initializing an empty array and setting it within the RNG for user mapping. We're iterating over that array and populating it with the array of random numbers were returned. But you see, before we do that, we're modding each number by 100, and that's because the random seed generated by VRF is a 256-bit number. So we're modding it by 100. So we'll end up with numbers in the range of 0 to 99. And just to kind of give another example, if you were to use VRF to say roll a die, you would mod it by 6, and then add 1 to get numbers between 1 and 6. This is just the final code snippet here. This is available in our docs. You can copy and paste this into Remix or your preferred IDE and start testing random numbers immediately. The only difference is we added a view function down here, which returns the array of random numbers for that particular username. This is just an example of what a contract creation and request would look like on the blockchain. So this particular request and response was done on Arbitrum Goerli testnet. As you can see, the bottom here is actually the request, and you see the response on the blockchain. There's a 2-block difference, and this took 3 seconds between request and response. So now we'll go into the use cases. Typically, a lot of our partners use VRF for GameFi, NFTs, online casinos, and participatory processes. Basically, any on-chain function where you need provably fair random numbers. So with GameFi, we see things such as tournament matching, in-game questing, loot box drops. With NFTs, you might want to use a VRF to randomly assign traits and attributes during the minting, or also to randomly distribute it to your players. As I mentioned before, the callback function, this is, with regards to NFTs, this would probably be where you would finish your mint in that callback. And then online casinos, pretty self-explanatory. Dice rolls, wheel spins, shuffling, dealing, poker, blackjack, they all need some randomness. And then it's also very easy to use VRF to pick a winner for lotteries and giveaways, or even select validators. Now we'll let Nolan take over, and he'll go over a tutorial implementing what we've just gone over. Let me stop sharing my screen here.
All right. One second while I get this all set up.
Nolan, don't worry. You can share your screen and you can take us through that by muting your cam. So it's fine.
So wait, the host they don't give you permission to enter because. Okay, yeah. Fine. Releasing.
I think Nolan's just getting set up here. In the meanwhile, are there any questions? I'm also going to take a look at the chat. Yeah, guest 956. Hello? Sorry, if you were asking a question, I can't hear you.
All right, I'm sharing my screen now. Is everyone able to see it?
Yeah.
All right, cool. Go ahead and get started then. I'm gonna go ahead and mute this tab.
Hello.
Okay. So Vinny mentioned that we're going to be going over an example implementation with an ERC-721 token. So what we'll actually be doing is just looking at how we can use our price feeds to validate the amount of ether sent to a minting function. So generally, we want some amount of ether sent to our contract. So say like 0.03 ether, and in turn we'll mint their token. We'll use price feeds to actually validate that the USD amount is correct. So we don't just have to set it to 0.3 ether. We can say, oh, whatever 200 US dollars is at any given time, whatever the pair is trading at, or whatever the value of the pair is. So if you go onto our docs, SupraOracles.com/docs, we actually have a bunch of development guides that are being put out. So right now we have 4. We have using our VRF to randomize ERC 721 traits. We have a collateral loan guide, and then monitoring smart contracts using Ethers.js, and then price feeds and payable functions, which is pretty much what I'm doing right now. We actually do have another one coming out that's an example of doing like a loot box, kind of like in GameFi with our VRF, which should also implement price feeds, but that will be out within the next like week or two. And we'll be doing videos on these guides too. So there's lots of content. Just check out our docs, check out the development guides. Yeah, they're pretty fun. I write them. If you have any feedback, feel free to like reach out to me in Discord, or if you have any suggestions, or even Telegram, but definitely prefer Discord since that's where I do a majority of the stuff. So rather than walking through line by line, I have the contract ready to go. So we're just going to walk through it step by step, what everything is, what we're doing, and how we can actually use these price feeds. So for our ERC 721 token, the only functionality we're going to be focusing on right now is going to be using the price feeds for validating the amount of ether. So we'll go ahead, we'll import OpenZeppelin's ERC 721 for our base ERC 721 contract. We'll implement counters, which is going to be used for stepping up our token ID, so we know which token ID is next to be minted when a user calls the minting function. And then we'll import ownable just so we can have access to the only owner modifier. If you don't want to use OpenZeppelin's ownable, you could, or counter, you could just write your own owner modifier. Better safe than sorry. So the most important thing here, you noticed, or Vinny mentioned it during his slides, is the iSuper value feed interface. That's like, I think if you take anything away from it, it's literally just look at this. So it has one function. It's our check price function, and you pass through a string, which is a market pair that we'll see down here in just a second, and it will return 2 values to you. It'll return the price and the timestamp. So the timestamp is just when that price value was recently updated, so like how new that data is. We actually won't be worrying about that, and this guy will just be focusing on the price. So the price value, it's int 256, and it's 8 points of precision. So we'll have to do some conversion later, but you'll see that within the valid amount modifier. So we'll go ahead, we'll initialize our contract, call it payable ether example. We'll say it is ERC 721 and it is ownable, so we can pull in that ERC 721 and ownable traits. And then we'll set up our counters variable. So we're going to go ahead and use counters for counters.counter, which is just importing counters from that opens up the counters contract, and we'll set it to a variable called token ID counter. We need an integer which will hold the USD value that we'll actually be checking against. So like I mentioned earlier, users are going to be able to say like, hey, our contract's going to say like, hey, you need to send 200 USD. Regardless of the price of ether, I just want 200 US dollars. That's what this value, we're going to be using this variable to check that. And then of course we need a super S value feed variable, an S value feed, to actually interact with this interface or with the S value contract. Within our constructor, we'll go ahead and we'll set up our ERC 721 token. We'll name the token SupraOracles with the symbol SUP. And then here is where we're going to kind of bind the contract address of the S value feed on chain to our S value feed variable within our contract, so we can actually call that check price function. So for this, if you check out our docs and you look at the getting started with price feed, there's a tab called network addresses where you can actually see all of the addresses that we're currently on, or all the addresses for the chains that we're currently on. So we have this page for both our price feeds and our VRF right here. You can also see the individual guides for each with some additional release notes on the graph. But basically what you'll do is whatever chain you're working on, you'll just copy this over and you'll drop it into the slot here. Alternatively, which would be better for production, is you actually pass this through as like parameter to your constructor. So you don't actually have to hard code that address in. So if you're deploying on multiple chains, you don't have to like go and paste the code. You can just pass it through on deployment. And the VRF, there's an additional step you have to do there, but you'll see that in the guide if you are interested in checking out the VRF. So moving on, we'll set the mint price to 100. I said 2 earlier, so we'll update that to 2. Why not? And now here's the 3 main things of this contract, aside from the interface that I mentioned before. So the 3 other main functions are 2 functions and 1 modifier. So we'll have a minting function, which will end up just calling the save mint function of ERC721, and then our withdraw function. So since a user is depositing Ether into our smart contract, we need a way to actually get that Ether out. Otherwise, it's going to be stuck there forever, and that sucks. We don't want to lose out on that Ether. I don't think anyone wants to lose out on some money. So now attached to the minting function, this is where you'll see our valid amount modifier. That's where we're going to be checking. We're actually going to be pulling the price fee value, doing the conversion, and then checking if the sent amount of Ether is valid. So, as you know, modifiers are executed prior to entering the function code. So this modifier will be totally checked before we get into any of this. So if at any point, if this require line returns false, then this exits out, the transaction fails, and we don't have to worry about actually minting the token. There's nothing to worry about. And the Ether they sent will actually be returned back to them. So it won't get burnt. It won't just get lost in the transaction. The require line returns any unused gas, any sent Ether back to the user. It just fails the transaction. So no harm, no foul. So first things first, in our valid amount modifier, we want to call the check price function from the S value feed. Here we're going to be getting the ETH USDT pair. So if you remember from our interface, this is just the market pair parameter that we're passing to the check price function. And if you go on our docs, you can actually see, aside from the network addresses, we have a page for all of the market pairs on every chain that we're currently on. We can see we have 2 Shardeum here, and you'll see every single market pair, every single ID for each. So you'll just want to use the ID to get whatever pair you want. So if you remember, that does actually return 2 parameters, but since we're not worried about the timestamp for now, we're just gonna comment and leave that one blank. It'll just get lost. Just go it to the wind, whatever. We don't need it. We only care about the ETH price that we're looking to get, and that is an integer. So now we have this price value, which is an 8 points of precision. So if ETH is currently at $1,500, I didn't check it today. I haven't checked it in a few days actually, so I don't actually know what it's at. But if it's 1,500, it would be 1500, and then there would be 8 trailing zeros after it. So we actually need to convert this to do all this math. We're gonna have to convert this to 18 points of precision. And the reason is we're gonna be comparing it to the amount of Ether that is sent to the user, which is in 18 points. So we're gonna have to get these into the same units. So right here, we'll bump that up to 10. We'll get that to 18. We have our minting price, which we currently set at $200 with no trailing 0 points of precision. Bump that up to 18. Now, we would normally just divide the 2, but we actually have to add on some additional zeros to account for both the math and the division. So the resulting required amount will be like units with the Ether that was sent. So both being away. Once we have that required amount integer, we're going to go ahead and compare it to the amount of Ether that was sent to the minting function, which is accessible through message.value. It's one of the global variables that's offered to us in code when someone initiates a transaction with our function. and then we'll just compare the two. And because required amount is an integer, we will have to cast this to uint. So you can see here, we're just checking to see that the amount of ether that's sent is greater than or equal to our required amount. So if the user sends 0.1 ether and our required amount for some reason is 0.2, it would return false. The transaction would fail. It wouldn't execute the minting code. And their ether and their unused gas would be sent back to them. If it was greater than, or if the two values were equal, it would approve, it would go through, it would mint the token. If the amount of ether was greater, it would go through, it would approve, it would mint the token. So let's go ahead and say, I've called the minting function and I've sent the proper amount of ether to this contract. So I am able to mint. What do we do next? First things first, we need to know which token ID we need to mint to the user. So that's where our token ID counter comes in from our trusty counters library from OpenZeppelin. So we'll go ahead and we'll grab the current value of our token ID counter and we'll store that within token ID. So at the start, we'll say, okay, hey, this counter is 0. So boom, this pulls a 0. Well, now we need to we need to increment this token ID counter so the next person doesn't mint the same ID. So we'll go ahead and we'll increment that before we call the save mint function, just for some security and safety measures. And now boom, the current value of the token ID counter is now set to 1, but I am holding 0 with my token ID, which is the token ID that I'm going to mint. And this is where we'll call the safe mint function of the ERC 721 contract that we imported from OpenZeppelin. And it requires 2 parameters. It needs to know which address we're going to be currently minting this token to and which token ID to actually mint to the user. So self-explanatory, boom, we want to mint them token, whatever the current token ID is that we pulled here. So in our case, it's the first call, it would be 0. And then we're going to mint this to just the caller of this function. So one of the global variables that we have is message.sender. And this value is just whichever address has initiated this function call will be stored within message.sender. So boom, we send them the token. And that's that. Once they've sent the proper amount of ether, it checks through the valid amount modifier to make sure it's the proper amount and then mints them the token. Boom, good to go. And then as we mentioned before, we do need a way to withdraw this ether. We don't want it to get lost and locked up forever. So we'll create a withdraw function that just accepts some parameter. And we want to make sure that only we can call this. So we'll tack on the only owner modifier imported from our ownable contract from OpenZeppelin, and then we'll just transfer the balance of this contract to whatever address we pass through. Alternatively, you don't have to send the entire balance of the address. You could have another parameter here that like takes in some value to actually like send, and then you would have to check to make sure that the contract has enough in balance. So that's pretty much it. It's really easy. I think a lot of people think it's a bit more intimidating than it actually is, but it's really only a few lines of code. You just need to import the interface. And also if you were putting this into production, you definitely don't want to just copy and paste this interface into like every single contract that you're working on. Like let's say you have like 3 different Solidity files or 3 different contracts that need to interact with this interface. It would actually be a lot better if you created some file within your project directory or within your like contracts, or within your project or contracts directory, and then you would just import the svalui.sol contract. So it would look like this. That looks even cleaner. Yeah, just for the sake of the guide, and we'll just leave it like this for now. So you really only need the interface. You really only need to call the check price function once, for our example at least, and you just need to initialize or bind the contract address of the svalue feed to your interface variable within your contract. Now, this was just looking at price feeds. I actually didn't plan on going over I actually have a full VRF and price feeds guide that I worked on for another workshop. So following this call, I'll toss that on GitHub, and then I can can like link it, or if you come into our Discord and ask for it, I'll link it in there, and then you guys can check that out, and you'll be able to see an implementation of both the VRF and the price feeds together. For now, why not? We might as well take a quick look at the VRF one as well. So this VRF guide is just VRF. This one doesn't actually include the price feeds. So similar to the price feeds, we're going to go ahead. We're going to use we're going to import ERC 721. We're going to import counters. And then we're going to set up our interface. However, this time, since the VRF, we need the super router interface. We need the VRF interface, not the price feeds one. And if you remember from Vinny's slides, the iSuperRouter contract has two functions that will be interacting. Well, it's two functions, really just one, just with different parameters on each that we're going to be interacting with. And that's our generate request. So the VRF is actually a request response model. So you need to request the number from the VRF service, and it will return it to your contract. So the VRF service actually needs to return that random number it's generated to, and that's where the function signature parameter comes into play right here. So this is going to be your callback function. So we're going to designate a function within our contract that's sole purpose is to accept the random numbers back from the VRF. We need to tell it how many random numbers to generate, how many number of confirmations to wait before we get this random number. And then this is an optional parameter, client seed, which just offers you some additional randomness if you want to try to make it unique to your contract. But it's totally optional. You don't actually need it. So moving on, just like the previous guide, let's set our contract up, inherit the ERC 721 with is ERC 721. Just like the other one, we need a counter to check what token ID we're looking to mint. So boom, set up our counters. And now this is where I mentioned that there's a slight additional step to the VRF. So you have two options with the VRF. You could either save the address of the VRF rather than just setting up the interface variable like we did here with the address, and then just call the function later, or so you can either save the address here and then create the interface later, or you can just set the interface here and just check the address of the interface later. But I'll get to that in a second. So for now, we'll just create an address variable, call it SupraAddr. This is going to store the address of the VRF router contract. So we'll slip over to our VRF docs, grab the contract address for whatever network we're working on. And in this example, we're actually passing it to the constructor. So SupraAddress just stores the address of our VRF contract. For this guide, for this VRF one, the idea is that every token is kind of like a player or a character. So we want that character to have some stats, that being 3 of them, level, health, and struct. So we'll just store that within player stats. This way, every single token has some unique traits to it, and these are the values that we'll actually be using our VRF to randomize. So when the user mints a token, what we actually want to do is we want to be like, hey, every token shouldn't start at like the same level or shouldn't have the same health. Let's use SupraOracles VRF to randomize a number, to randomly assign these traits at the time of minting. And again, that doesn't have to be at the time of minting. It could be totally whenever you wanted. You could do it later in some additional function, like a level up function that also randomizes some traits. But for now, we're just going to do it initially when they mint. So now we need 2 main mappings to make this VRF thing work. So our first is going to be nonce to minter address. So this is a uint 256 to an address mapping. And you'll see up here, our generate request functions actually return a uint 256, and that's the nonce. So the nonce of that request is what the VRF is going to return back to you when you make the request, or that generate request function is gonna return back to you. And we need that nonce to pair the response to our request. So let's say I make a request and it returns the nonce value of like 10. So it's like, hey, the nonce of my request is 10. When the VRF responds with the random number to my callback function, it's actually going to give me the nonce value. So the VRF sends the random number to my callback function with one of the parameters being the nonce. So we're going to use that nonce value to map the two together, to pair the two together, because since that response call is coming like a second after or a block after, it's going to be two separate function executions. So we need a way to like tie those two together. That's what the nonce is for. So then we'll have just a mapping, and all this mapping is mapping our token ID to the player stat struct. So we know. So basically, what we're saying is every token has a player stat struct tied to it, so we can get like the stats for that token. So realistically, you only need this one mapping for the VRF to work, and this is just like arbitrary to our use case, or like just for our use case. So far, the only thing that's been associated with the VRF is our interface, setting up our address, and then this nonce dementor. So let's take a look over at our constructor. Realistically, is the same in essence to the previous guide. We'll just set up our ERC721 tokens. This one, I'm calling it random traits with the symbol wrap. And we're accepting a parameter. Like I mentioned, if we accept a parameter for our contract address for like the interface we're working with, whether it's the price feeds or the VRF, it helps with deployment. So rather than hard coding the address in like here, multiple chains, we just pass it through all at once. So we pass through the VRF contract address that we're working on to our constructor, and we'll store that within the Supra address variable, and we'll use that later, or in just a second. So now we have 4 functions remaining, and I'll just run through them real quick before I like step through each code. So we have the minting function, which is actually going to act as our request function. We have a finish mint function, which is going to act as our callback function. So the minting function is our request. We say to the VRF service, we say to the Supra router, yo, I need a random number. What do you got for me? And then the VRF says, hey, here's your nonce. I'll get back to you in like one block. Give me like just a second to get that random number for you. And then our network picks up that request, says, okay, where's this callback function? Okay, he passed me finish mint with these 2 parameters. Let's send the random number back to that callback. So it sends back the nonce, and then it sends back this array of uint 256s, which is an array of random numbers. So if you request one random number, you'll still get an array. You'll just have to get position 0. If you request 2, it'll be 0. So if you do request more than one, you are going to have to like set up some loop to like iterate through it. But for this example, we're actually only requesting one. Then we have 2 more functions. We have a get token stats, which is literally just the view function. These 2 are just like some bonus functions that I like set up for the guide. Like you don't actually need these for the sake of the VRF, but the get token stats is just going to return the stats of the token. And then this one is just an example of like how you would allow a user to level up a token, like if they reached a certain XP cap in your game. So anyways, slipping back to the minting function, which is our request. This is where we're going to call that generate request function. It does return the nonce, so we'll set a nonce value within this minting function equal to the return value of the generate request function that we can call through the iSuperRouter interface. So all we're doing here, this line right here, would be equivalent to us, like within our constructor, saying like, and then we would have to have like a iSuperRouter variable up here. So if you remember in the price feeds one that we just looked at, we actually just set up the value feed interface variable within the constructor. You can do that too. Now we're just storing the address, so we'll have to set up that interface here. So every function call, we bind it we bind this address to this interface, and then we call the generate function of the interface. So we're requesting one random number within one confirmation with a client, an optional client seed of 1, 2, 3. So granted that is optional, so we could just totally remove it. And now, as I mentioned before, for this nonce to minter address mapping, the nonce is our key player here in mapping the two requests and responses together. So we'll store that value within the mapping. So for whatever nonce this is, so for like if we get nonce 10, we want to say that the address that belongs to nonce 10 is the current sender of this transaction. So access the global variable message.sender. Whoever called this minting function is the person that requested this random number. So nonce 10 belongs to message.sender. Nonce 10 is my address or the caller's address. So now, boom, VRF has picked it up and they're ready to send it back. And this is where the callback function comes in, like I said. So we have finishment with two parameters, the nonce and RNG list. And this is one of the most important lines that you cannot forget right here. So are you thinking like, oh, hey, if I have a function within my contract that's external and it's used to deliver random numbers to like set some token values or like mint some tokens, I should probably have some access control on that. Otherwise, anyone and everyone's going to be able to call it. So we need to restrict who can call this function, and we only want it to be the super router service. So we don't want anyone other than the super's VRF to return values to our callback function. So we just require that the sender of the call to the finishment function is equal to the super router address. So only this address is going to be able to call our callback function this way. Only the super VRF service can return random numbers to our contract. If you forget that, people will terrorize you. So do not forget this. This is very important. Access control. Alternatively, if you had multiple callback functions, for whatever reason, you could set up a modifier called like only VRF Supra is awesome. And then you would just tag that modifier onto your callback functions, and then you wouldn't need to write this line over and over. But anyways, moving on. Like I said in the previous example, we need to know which token ID to mint. So boom, let's go ahead and grab the current ID of our counter. Let's increment that up so the next person can work with whatever they're working with. And now it's time to call the safe mint function. So as expected, the second parameter is going to be the token ID, and the first parameter is going to be the address. But hey, in the previous example, when we looked, we were actually minting to the message.sender. But the thing is, the message.sender value of the callback function is actually going to be the VRF contract. So since the VRF is returning the random number to our callback, they're going to be the ones calling that callback function. They're going to be the ones calling finish mint, which means that message.sender, we can't use that message.sender value because it's the super router address. So this is the second end of the pairing with the nonce. So like we mentioned earlier, we use the nonce to bind the request and response together, and that's where this comes into play, to bind the response to the request. So here's where we stored the nonce and address. Here's where we're actually using that. So for the current nonce that's been returned, so whatever nonce this response belongs to, mint it to that user. Grab that address from them. And now, boom, we've minted the token. We successfully made a request, received a response, and then paired the two together. But now we actually have to use the random numbers. So for this example, since I've only requested one random number, I just know that it's going to be just position 0 within my RNG list array. If you had multiple numbers, like let's say you requested either 3 or 4, I would suggest setting up a for loop to just kind of iterate through the length of the array, rather than like hard coding in like 1, 2, 3. Yeah. But it's totally your design, totally your implementation. So the token's minted, and all we're doing now is we're going to use that random number to set it to set like some random values. So we can actually use a single random number more than once, or like for more than one thing. So let's say we have this like really long random number, 78 like numbers or whatever the length of it is. If we're not using the full length, let's say we only want to get like 2 random numbers, we can use a combination of both modulus and division to pull multiple numbers out of it. So let's say you have this like really long number. That's like you have 998877. Basically, what we're going to be doing is we're going to be grabbing 77. We're going to be grabbing 88. We're going to be grabbing like 99. So we're able to request one number, which would actually look like this. It's super long. Use it more than once. So we'll go ahead. We're going to set the token, the level of the current token ID. So we're going to use our token ID to stats mapping to access the level value stored within the player structs for that specific token. And we're going to set this equal to a random number between 0 and 99. So technically what's happening here is it's taking that really long random number, forming some modulus on it, and it's going to say, give me the value of 0 to 99. And then we'll do that same thing again, but this time we're going to do it by 10,000, and then we'll divide it by 100. So this modulus 100 would end up grabbing 90 in this number example here, where this modulus 10,000 divided by 100 would end up grabbing 78. So what this would actually do, second line here, this modulus 10,000 would actually end up returning you like 7890. And then you just divide that by 100 to shift the decimal over, to shift it over 2 places, and you just result with 78. So there you can see kind of like the craftiness between the modulus and division to grab these numbers. Now, that only works so cleanly. Like, oh, look, 90's at the end, so we're just grabbing 90. Like, we're just grabbing that only works because we're doing modulus by 100. If you're doing it by a different number, it wouldn't be as clean. It wouldn't look as cool or obvious. But since we are setting our traits between the value of 0 and 99 or up to 100, this works out perfectly for our use case. So grab a first random number from it. We'll cast it to UN 8 because our level health and strength are all UN 8. And then we'll just store those within level health strength. So now it's done. We've successfully set up our interface, successfully made a request, successfully received a response. We've paired the request and response together. We've minted the token, and now we've set the random values of that token. So now that's done. Your token's minted on-chain with its stats available on-chain. If you wanted to generate some metadata, you would just have to write some script that would call the contract to generate some metadata file, or you would have to set up some application or some API that would like serve the metadata to whoever was seeking it by calling your smart contract in real time to generate that data, generate the metadata. Everything's on chain now. So now we just have those 2 bonus functions I talked about. We need a way for people to actually access the values of their token stats. And that's where this view function comes in. So they'll pass through a token ID, and we just want to give them the level, the health, and the strength of whatever token they're requesting. And then the next one is like a level up token function. So I would imagine this is called like in a GameFi project. Like, let's say I just killed like 2 spiders, or let's say I'm playing Minecraft and it's like, I just killed a zombie, I just killed a skeleton, and I've like picked up their XP. Boom, I've leveled up to 2. Like, in the MT world, like maybe when I hit 2, rather than just like getting XP to do some enchanting, I now want to like level up my stats. So level up token's called whenever you decide. We'll just check to make sure that the token exists. So we're like, hey, does this token exist? Because if this token doesn't exist, I don't want to I don't want to update its values. So we go ahead and check to make sure it exists. And then we'll just we'll just increment the level by 1. We'll say, hey, every time you level up, you get 10 health. And every time you level up, you get 10 strength. So if you notice, the only like check I have in here is does this token exist or not, using the exist function that's within the ERC 721 contract that we imported from OpenZeppelin. You might want to add some access control on this one as well, because right now the way this is set up, since anyone can call this, any external resource can call this, like I could just keep calling this function over and over and just keep leveling up my token. So you might want to add some, like, add a modifier in here or add some access control where it's like only game system. And I imagine like this game system modifier or this only game system modifier is something that you've set up so only your game's like contract address can actually call this level of token, or you can make it internal and set up some internal process. But yeah, that's really it. Both price feeds and VRF, they're really easy. If I made it any, if there's anything that's confusing, or if you found anything a little tricky, or just you want to ask some questions, again, please feel free to jump in our Discord server. One of my, something I love and I'm really passionate about is just like sharing information with the community, and that's actually part of my job. So, it's no burden to me if you want to come in and ask some questions. Actually, that's what I'm supposed to do. So that's what I'm here for. Feel free to use me as a resource. I definitely prefer Discord over Telegram, and we're trying to funnel more users into there. So you could do that. That'd be great. Just let me know that you're sitting in on this call. Maybe we'll figure out like a special role or something. Yeah, that's it for the guides. Like, please check out our docs. Go through them more. We'll have more coming out very soon, more in the future, some more videos, and I'll be putting all these contracts, all this code up on a GitHub repo really soon. We're just working on like what repo we want to store that in, but we'll have that in the next couple weeks.
Thank you so much.